So let's talk about the butterfly effect. You've probably heard the term before, maybe in movies or books, but it's so much more than just a cool idea. It's a real scientific principle that explains why some things are just fundamentally impossible to predict.
You know, it all starts with something incredibly small.
I mean, a difference so tiny that you might not even be able to measure it in the first place.
And that one seemingly insignificant detail, it can grow and multiply until it leads to a future that is completely different from what it would have been. And I don't mean that as a metaphor, it's a mathematical reality.
Okay, so how does that actually work? How can a tiny, almost invisible difference have such a huge impact on the future of a whole system?
Well, to really get this, we have to start with the core scientific idea that makes the whole thing possible. So the official name for the butterfly effect is sensitive dependence on initial conditions. It sounds a bit complicated, but the idea is actually pretty simple. Imagine you have two situations that start out almost exactly the same. Well, in certain systems, they don't just stay a little different. Over time, they will drift apart until their futures are completely unrecognizable from each other.
But here's a really important distinction to make. This is not the same as randomness. The systems we're talking about are what we call deterministic. That means they follow very strict, predictable rules with absolutely no chance involved. And yet, even with those perfect rules, we can't predict what they'll do in the long run. And that paradox, that's what's known as deterministic chaos.
So where did this whole idea even come from? Well, like a lot of big discoveries in science, it was stumbled upon almost completely by accident. Let's dig into the story of the man who first saw it happen.
Our story starts back in 1961 with a meteorologist named Edward Lorenz. He was using an early computer to run a simulation of the weather, using a set of equations to model how things like temperature and wind speed change over time.
So one day, Lorenz decided to rerun a simulation from the middle to save some time. But instead of typing in the full 6 decimal place number from his printout, 0.506127, he just typed in a rounded version, 0.506. I mean, the difference is tiny, less than 1 part in 1,000. He figured it wouldn't matter at all.
But the result? It was shocking. At first, the new simulation looked just like the old one. But then, little by little, the two graphs started to drift apart. And after just a couple of simulated months, the weather patterns were completely different. That tiny rounding error had created an entirely new future for his digital weather.
And this is where Lorenz had his big aha moment. He realized the problem wasn't with his computer, and it wasn't with his math. The problem was with measurement itself. In a complex system like the weather, you can never, ever know the starting conditions with perfect accuracy. And any tiny error, no matter how small, will eventually grow.
So that brings us to the key question, right? How exactly does a tiny, insignificant error grow into something so massive? It doesn't just add up slowly, it actually multiplies on itself.
The first ingredient is a concept called nonlinearity. Think of it this way. In a simple, linear system, if you double the input, you double the output. It's predictable. But in nonlinear systems, all bets are off. A small push might do almost nothing, or it could trigger a huge, totally disproportionate reaction. And you can't tell which it's going to be ahead of time.
The second key mechanism is something called a feedback loop. This is when the result of an action feeds back and changes the conditions for the next action. For instance, a tiny change in temperature affects the air pressure. That changes the wind. But then, the new wind pattern can circle back and change the temperature again. These loops take that initial small error and just amplify it over and over.
And when you combine nonlinearity with feedback loops, what you get is called exponential divergence. Two paths can start so close they look identical. Then they begin to drift apart, slowly at first. But pretty soon, that separation speeds up until they're headed in completely different directions, ending up in totally different places. The error doesn't just add up, it multiplies.
Now, this whole idea isn't just some weird quirk you find in weather simulations. Its discovery showed us that there's a fundamental, built-in limit to our ability to predict the future in a whole lot of different areas. We see this kind of chaotic behavior all over the place. Of course, it's in weather systems, but it's also in the incredibly complex web of ecosystems, the unpredictable behavior of the stock market, and even in something as simple as a double pendulum. It turns out you don't need a huge, complicated system to get chaos.
And here's why this all really matters. For systems like these, Perfect long-term prediction isn't just hard, it is physically impossible. You know why a weather forecast gets unreliable after about a week or so? It's not because our computers aren't powerful enough. It's because even if we had perfect models, those tiny, unavoidable errors in our starting measurements will have grown so huge that the forecast is basically just a guess.
So, this discovery really forces us to separate two ideas we usually connect: determinism and predictability. A system can follow exact, perfect rules with no randomness whatsoever and still be completely and fundamentally unpredictable over the long term.
So the ultimate takeaway is this. In these chaotic systems, the future depends on details that are just too small for us to ever measure perfectly. The flap of a butterfly's wings doesn't literally cause a hurricane on the other side of the world, but it stands for one of the infinite tiny variables that, when amplified, will always end up shaping the final outcome.
And that leaves us with a final, pretty big thought to consider. We live in a universe that seems to run on fixed, consistent laws. But the very nature of those laws means that its long-term future is impossible for us to ever know for sure. So, what does that inherent unpredictability mean for how we understand the world and our place in it?